The title of this lesson is HOM VW. That's the notation. And as we said at the end of the previous clip, here's the idea. We have two vector spaces, V and W. Okay? We know what a vector space is. It's an algebraic structure. It satisfies some axioms. Once we defined vector spaces, we moved on to define linear maps between vector spaces. So functions between one vector space and the other. Okay? So there were vector spaces, then there were functions between vector spaces. Now we're going to look at all the functions between two vector spaces, and we're going to claim that in itself, this is just a notation for all the linear transformations between V and W. I'll write it in a minute. We're going to claim that this is in turn, again, a vector space. And we're going to say precisely what it's isomorphic to. We're going to know how to think of this vector space in terms of something very tangible, something we know. Okay? So here goes. So first, the basic definition. Let V and W be vector spaces over some field F. The collection of all the linear transformations, all linear maps from V to W is called and denoted HOM VW. This word HOM is short for the word homomorphism. Okay? So in general, in complete generality, when V and W are any algebraic structure, this can be defined. These can be two fields, these can be two groups, these can be two any algebraic structures, and we look at the appropriate maps that preserve the structure, and those are in general called homomorphisms. Okay? And the appropriate maps from vector spaces have a specific name, which we call linear maps or linear transformations, but they're just the homomorphisms in the context of vector spaces. Okay? And this in general is denoted by HOM VW. All homomorphisms, when these are vector spaces, the homomorphisms are linear maps. That's the correct notion of a homomorphism between two vector spaces. Okay? But you may see this in various contexts, not just when these are vector spaces. Okay? Okay. So let's think first. So here are a couple of facts. So here's the first theorem. So what are the elements here? This is a set right now. A set. There's no structure on it. It's just a set. It's a bunch of elements. Each of these elements is a linear map from V to W, right? Okay. Can we put a structure, can we impose a structure on this space? What is a structure? We need to define operations. So we have elements here, maps from V to W. Do we know any operations between maps? The answer is yes. We can add linear transformations. We know how to do that, right? We know how to add what is T plus S on an element V. It's T of V plus S of V. We defined it, right? We know how to multiply a linear map by a scalar. What is 8 times a linear map, right? It's just take 8 times what the linear map does, okay? So this space has 2 operations at least. We know there are more, right? We can, well, not always, right? But sometimes we can compose. If V and W are the same, then we can compose. But in general, we can't. But always, we can add and multiply by a scalar. And those operations of adding maps and multiplying a map by a scalar, in fact, give this space a structure of a vector space. Okay, so let's write that. HOM VW the set of all linear transformations from V to W is not just a set, it's a vector space, is a vector space over F, over this field F. Okay, with respect to, let's write, with respect to, we need to say, we know what the elements are, they're the maps. We need to say what are the operations to addition of linear maps and scalar multiplication of linear maps. Okay? So what would be the ingredients of proving such a theorem? And I'm not going to do it. It's tedious in a sense, but in fact it's very straightforward. What do we need to show? Well, there was a list of axioms of what it means to be a vector space. And this is not a subspace of some bigger space where all we have to check is closure under addition and scalar multiplication. It's a new vector space with new operations. We just have to check all the axioms. So for example, if we do t plus s, is it the same as s plus t? Okay, when we do alpha times t plus s, is it the same as alpha t plus alpha s? Okay, is there a zero element? Okay, and what's the zero element here?
Zero.
That's always a correct answer, but what's the zero element here?
The kernels?
The kernel of what? Well, if you're going to answer that question, before answering what's the zero element here, you have to answer what are the elements here? What are the elements here? Linear maps. So what's going to be the zero element here? The zero map that sends everybody to zero. Okay? Good? So it's really just a matter of pausing and thinking and not being afraid of abstractness. Okay? And then it suddenly becomes very simple. All you need to do is check that it satisfies all the axioms of being a vector space. Okay? And the elements are maps from V to W. We know how to add maps. We know how to multiply a map by a scalar. Just check that all the axioms in fact hold. And they're straightforward. We know them. We know that when we add two maps, t plus s, it's the same as s plus t. It's going to give the same map between V and W. Clear? We know that it's closed under addition, for example. Right? If we add two maps, if we add two linear maps, it's again a linear map. Right? That's all it means to be closed under addition. You add two guys here are linear maps. Again, you get a linear map, an element here. Okay? So that's what you need to do. Check, and it's really checking like a checklist of the properties. You have to recall what are all the properties, so this is a good exercise, to recall what are all the properties of being a vector space and verifying that they indeed hold. Okay. So I want to remind you of a theorem that we had. And the theorem said that, so recall that there was a relation between linear maps and matrices. Okay, what was the relation? Given a linear map, choose a basis. You have a matrix which represents that linear map with respect to that basis. Given a matrix, it gives rise to a linear map, right? So if you have a matrix, you can construct a linear map that corresponds to it in the sense that if you take that linear map and find its matrix representation, it's going to be that given matrix, right? So it goes both ways. In some sense, linear maps and matrices are the same. What I want to do is say that now formally. Okay? So I'm going to write the ideas, how I'm getting there, but the statement in a minute is going to be the space of linear maps, Ham VW, is isomorphic, we now know the word, to matrices. Okay? As linear spaces, they're the same. Matrices and linear maps are two ways of looking at the same thing as far as linear algebra goes. Okay? So recall that if T and S are maps from V to W, and E is a basis for V, and F is a basis for W. So we have two linear maps, T and S from V to W linear. If T and S, we don't need these. If T and S from V to W are linear, and E is a basis for V and F is a basis for W, then we can take the matrix representation of T and of S and of the sum T plus S, right? And the properties are conserved in the following sense. If we take T plus S and take its matrix representation with respect to the two bases, E and F. Remember that? Okay? So remember what we do, how we take a matrix representation. We take the bases, let the transformation act on the basis. We get something in the range, in W, and write that as a linear combination of the little f's, and then take the transpose. Remember that? Okay. So what we had is that this equals T, E, F plus S, E, F. Okay? We proved that. Or maybe we didn't prove it, maybe we just said it and gave examples. I don't even remember. Okay? And likewise, if we take alpha T and take its matrix, the matrix that represents it, that equals alpha time the matrix that represents T. Okay? Remember this stuff? Okay? So the relation between adding, this plus is a plus of linear transformations. That's the plus in Hom VW, right? This plus and this plus, which is a plus of matrices, okay, satisfy this property. Okay? And what does this property mean? Let's think of it for a minute. Okay? This requires some being one step further in your mathematical thinking. Okay? It's in a sense abstract, but I think you're ready for it. I really think you're ready for it. So the statement is that the map that takes linear transformations to matrices, the map that takes linear transformations to matrices is a linear map. You add linear transformations, matrix, it's the same as matrix and then add. You multiply a linear transformation by a scalar and then matrix, it's the same as matrix and then multiply by a scalar. Okay? So this is something that we proved, but this means that the map that sends T, a linear map, to T, E, F, the map that sends a transformation to its matrix representation is linear. How many of you are with me? Raise your hand if you're with me and not completely lost with, okay, that's good, that's good. Okay, so good. I know it's a bit heavy. It's a bit heavy because it's a bit heavy. Okay, good. Okay, so let's.
It's that heavy because we already went through that a couple of times in that notation. So that's.
It's heavy. It's heavy, but you're with me. Okay, saying that it's not that heavy is, it's heavy. It's heavy at this point. Okay, and in fact, as I mentioned, this specific lesson that we're discussing right now about Ham VW is not always even in the material of this specific format of Algebra 1. Okay, so we have this space Ham VW whose elements are T's, linear transformations. We have another space n by m matrices whose elements are matrices. And we have a map going from Ham VW, sending T's, to matrices, to their matrix representation. Okay? And the claim is that that map is itself a linear map. Okay, so again, we took one step up. Okay, so let's write that. So the map that goes from, maybe we'll give it a name. Let's see if I want to give it a name. Yeah, let's call it phi. The map phi going from Ham VW to matrices m by n matrices over F, where m is the dimension of W and n is the dimension of V, right? Those are that's the range. Okay, the representing matrices are m by n. The way we get them is we transpose, right? The writing T of elements of V as linear combinations of basis elements of W. Okay, so it's not n by m, but rather m by n because we transpose. M is the dimension of W and n is the dimension of V. Okay, so this map, maybe we should write. So m is the dimension of W and n is the dimension of V. This map, and what is the map? The map is just the map where phi of T is an element here, is just its representation matrix, T, E, F, with respect to two fixed bases. E and F are data for this business. Okay? So this map between two vector spaces is a linear map. Is a linear map. That's what we just argued. Okay. If I can show that it's one-to-one and onto, then these two spaces are isomorphic. Okay? So we will show that phi is one-to-one and onto, and conclude that Ham VW is isomorphic to matrices, to m by n over F. Okay, so showing that it's one-to-one and onto amounts to showing the following two things. One, the only way to get the zero matrix is if you start with the zero transformation. That's rather obvious if you think of how we construct this matrix, right? how do we construct this matrix? We take basis elements here, do t to them, write each of them as linear combinations of W, take the coefficients and transpose. Remember? That's how we constructed the matrix representation. The only way to get all zeros, we're going to write that. We're going to write it formally in a minute. The only way to get all zeros is if we started with the zero map. Okay? So that's going to be proving that it's one-to-one. Proving that it's onto is, suppose you start with a matrix, A, any m by n matrix. Can you find a linear transformation such that its representing matrix is that given A? And that is again something we did at least in an example. Remember when we started out, when the first example that I gave you of a representing matrix was a linear map going from matrices to polynomials or something like that, whose representing matrix was the famous matrix that we know from the system of equations, that the matrix that's been running along with us very long ago. Remember that? And that's precisely the way, when you have a matrix, that's the way to construct a linear map. Okay? And the way to do it is just impose what you wanted to do to basis elements. That determines the map. Remember that? Okay, so all these ideas we've seen already, we just have to formalize them a bit more. It's not going to be very complicated. It's going to be things that we've seen, at least in examples. Okay? But what's heavy here is the terminology, the abstractness of going one step up. This is a space, a vector space, whose elements are linear maps between vector spaces. Ouch. This is a space of matrices. They're isomorphic, meaning that there is a linear map between these two vector spaces, and here it is. It's precisely this. Good? Raise your hand again if you're with me. I have to know if I'm not losing people. Great, great.
I have a question there.
Yeah, sure.
You said that if the dimensions of both spaces are equal, then they're isomorphic.
Right.
And
We can rephrase this statement in terms of dimensions. Okay? And we can write that as a theorem, and conclude that these two spaces are isomorphic, or equivalently, I don't know if this is what you meant. I'd never let you finish the question, but maybe it is, and if it is, it's great. It's a great observation. Or equivalently, that the dimensions of these two guys are the same. Right? That would be the statement. And this is sometimes how you would see this exact theorem. The dimension of Hom VW, the dimension of the Hom space, the dimension of the space of linear transformations between V and W, is precisely the dimension of this space, which is m times n. That's this dimension. Therefore, it's the dimension of V times the dimension of W. This statement is an equivalent way of saying this statement, right? Because they're isomorphic if and only if they have the same dimension. Do you agree? And both of these you may see as theorems, and they're the same theorem. You prove one, you automatically prove the other because of what we said. I think they deserve boxes. In some sense, this is really I don't know, the furthest this course goes. This is like the most. Okay. This is precisely the statement that linear transformations can be implemented by matrices, and that this implementation is in fact not just a implementation, but it's an isomorphism. Matrices are linear maps. Linear maps are matrices. As far as linear algebra is concerned, they're the same thing. If you talk to people working in linear algebra, you could, in the same conversation, in the same paragraph, see them refer to once a matrix, once a linear transformation, and for them it's the same thing. Okay? They are the same thing. That's the meaning of this. Was that your question?
Yeah.
Good? Okay, everybody, ask. Ask if it's not clear. Okay, so let's write that. So let's write the proof. So let's just recall what we want to write. All we want to show in order to prove this theorem, or equivalently this theorem, right? Two spaces are isomorphic if and only if they have the same dimension. That's something that we proved in the previous lesson. So in order to prove one or the other, all we need to show that there exists an isomorphism between these spaces. And we already said what that isomorphism is going to be. Okay? It's just going to be the map sending a matrix to its matrix sending a linear map to its matrix representation. Okay? It's linear because of the previous theorem, right? Let's look again at this board. It's linear because of this theorem. Sending a linear transformation, adding and then taking the matrix, is the same as taking the matrices and then adding, right? So it's a linear map. It's a linear map. All that remains to show is that it's one-to-one and onto. Good? And then we have these two theorems. So let's do that. So phi is, what are we going to start with? One-to-one. Why is phi one-to-one? So let's prove, we will show that the kernel of phi is 0. That's how we prove that a linear map is one-to-one. Okay? So how do we do that? And once we understand what we are doing, doing it is rather standard in this case, rather standard. So we need to show that the kernel is 0. How do we show usually that the kernel is 0? We take somebody in the kernel and show that it's forced to be 0. It can't be anything else. So what am I going to call somebody in the kernel? Give me a letter name for it. T. It's a linear map, right? Elements in the domain of phi are linear maps. They're elements in Ham VW, right? So let T be an element of the kernel. T is a linear map. Good? Okay. So what does it mean that T is in the kernel of phi? It means let T be in the kernel of phi. So phi of T is 0. That's what it means to be in the kernel, right? What is phi of T?
It's a matrix.
It's the matrix representation of T, right? i.e., so this is just a different way of saying the matrix representation of T with respect to these two bases is the 0 matrix. This is the 0 matrix, right? 0 matrix. Good? Okay. But let's recall how we build the matrix representation, right? How do we construct the matrix representation? Recall. What do? We take the elements of E. Let's call the elements of E little ei's, E1 through E. What's the dimension of V? It's n. So it's E1 through En, right? We do T to them. So we take T of E1 up to T of En. And we write each one as a linear combination of the elements of F, right? So and then we take transpose. Do you agree? So if the matrix turned out to be the 0 matrix, the 0 matrix, it means that the coefficients of T of E1 were all zeros. 0 F1 plus 0 F2 plus ... plus 0 Fm. Do you agree? Because then we took all these, transposed, and got the zero matrix. So they all had to be zeros, right? And likewise, all the way up to here. 0f1 plus 0f2 plus dot, 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 plus 0fm. Do you agree? Okay. The only way of getting the zero matrix is if all the coefficients were zero, because that's how we get the matrix. We take a transpose of the coefficients. These coefficients in blue are the first column of the matrix, right? And if that is a zero matrix, all the coefficients are zero. Do you agree? Okay. So what does it mean? If for each of the basis elements of V, T of it was zero. Okay, this means that T of E1 was in fact zero. And all the way up to T of En, all of these were just zeros. So what T does is it takes all the basis elements of V and sends all of them to zero. So what does T do to a general element? Send it to zero, right? So therefore, T of V, which equals T of alpha 1 E1 plus alpha N En, is 0. So for every V. Good? So the map is 1-to-1. You take an element in the kernel, it has to be 0. If somebody gets sent to the zero matrix, it had to be the zero map. Okay? Okay. How do we prove that it's onto? We need to prove that it's onto. And again, it's rather straightforward once you know what you want to write. Okay, so phi is onto. So what do we need to show? So let A m by n be a matrix. Be a matrix. We need to show that it's phi of some map, right? Let's once again look at phi. Phi is the map sending linear maps to matrices. Now we're starting with a matrix. We want to show that it's the matrix representation of some map. We have to define what is that map. What was T? Okay. So again, we're going to resort to our knowledge of how this map works, how we get the matrix representation. We work on a basis, transpose, right? That's the idea. So let's do that. So if we start with a matrix, let's find a linear map, T in Hom VW, a linear map, such that phi of T, which is just the representing matrix with respect to these two bases, is A. Right? That's what we need to do. Do you agree? Okay. So define, I'm going to construct it. I'm going to tell you precisely how we're going to do it. So I'm going to tell you what T does to E1. I need to tell you what T does to E1. I'm going to define a T. I'm finding a T. What does T do to E1? It writes T of E1 as a linear combinations of the little f's, right? Something f1 plus something f2 plus something dot 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 plus something fm, right? What are these something going to be? Well, these are going to be the first column of A, right? Because when I transpose, I should get A. So if A, let's call A, Aij, right? That's just giving names to its elements. So T of E1 is going to be A11 times F1 plus, and I want the first column, so Fn M is going to have a M1. That's what I want T to do to E1. That's how I'm defining T. And T of E2, I'm going to define it as a 1, 2 F1 plus dot, 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 plus a M2 Fm. All the way to T of En is going to be A1N F1 plus dot, 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 AMN Fm. That's how I'm defining what T does. I'm defining what it does to basis elements of the domain, of V. Okay? So if T does this, what is going to be the matrix representation of T? If T, by definition, does this, what is the matrix representation of T? It's take the coefficients, all of them, transpose. That's A. Do you agree? That's how we construct a map whose matrix representation is a given matrix. Okay? And then, indeed, T is linear. Why is T a linear map? I just said it does some magic. How do I know that it's a linear map?
Because it can be represented by a matrix.
Okay, that's one way to look at it, but there's something even more basic. We said that if we define what a map does to basis elements, it determines what the map does to everything as a linear map. Okay, so then indeed T, it's not that T is linear. I didn't define T completely yet. I just defined what it does to basis elements. Then T, maybe we should write it more precisely.
T or phi?
T. I'm defining T whose phi is A.
But isn't T linear by definition because we said that it's in Hom VW?
We're looking for a T in Hom VW. We said let's find T in Hom
So we
VW.
need to prove that the T that we defined is linear before we can...
Right, and in fact what I'm saying is, if we want to be completely precise, we didn't define T yet. We just defined what T does to E1 through En. Okay? Then indeed T gives rise to a linear map. T of some vector in V is going to be, write the vector as a linear combination of these, and then take the linear combination of the images, right? When T is defined on a basis, it fixes T on the entire space. Okay, so T gives rise to a linear map. I can add it by T of some vector V is T of, write the vector V as alpha 1 E1 plus dot 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 alpha n En, and define that to be alpha 1 T of E1 plus alpha n T of En. And these are defined. That's what we defined, right? So once we define T on a basis, it fixes T as a linear map. Okay? So T gives rise to a linear map whose matrix representation is precisely A by construction. Whose, to a linear map whose matrix representation is A. Good? So that proves that phi is onto. I know this specific lesson is a mouthful. It takes somewhat more maturity to absorb these details. Okay, I think you're there, at least by your responses of raising your hands when I asked who's still with me. It looks like you're there, but you may need to go home and think about this a bit more. Okay, we did pass on to to a higher level. Okay? So let's recall what we did here. We defined Hom VW as the space of all linear maps. Okay? And we said that it itself is a vector space with respect to operations on linear maps. Okay? Furthermore, there's a map between this vector space to matrices given by phi of a map is its matrix representation, and this correspondence between the two is a linear map, which is one-to-one and onto, and therefore is an isomorphism between these two spaces. Okay? Thinking of linear maps or thinking of matrices, as far as linear algebra goes, they're the same thing. Every linear map is, and remember when at the very beginning, our first example of a linear map was multiplying by a 2x2 matrix. And then I said, well, this is just a spoiler for the future, but any linear map is in fact multiplication by a matrix. Okay? And now we're finally, at the very end of our discussion of linear maps, saying, indeed, that's the case. Any linear map is indeed a matrix, and vice versa. In the linear algebra way of saying it, they're isomorphic. Okay? And in particular, this gives rise, or this is equivalent to a statement about dimensions. Okay? So how many linear maps are there between two spaces? How many different linear maps are there between R4 and R3 of X? How many linear maps are there? Answer, well, at least you know the dimension, right? So the number, a basis for all these different linear maps, okay, the dimension of this is 4 times 4 in that case. I gave an example of two spaces with dimension 4. Okay? So this and this are equivalent statements because two spaces are isomorphic if and only if they have the same dimension. Good? Okay, so think of this a bit more. It's there in all our examples, right? We did many examples where we translated linear maps to matrices and translated matrices to linear maps, but now it's finally the abstract statement that, in fact, it's really a dictionary. It's really thinking of two seemingly different structures as the same thing. Good? Okay. So what we want to do next is return to earth a bit, okay, and discuss things which are more explicit, much more explicit, and something that we have mentioned before as well. Given a linear map, we can have many matrix representations, depending on the bases that we choose, right? How do we find the best one? And the best one is going to be the one for which the matrix representation is easiest to work with. For example, has as many zeros as possible. That's a matrix that's easy to work with. Okay? So remember, this is not unique. Okay? This is unique once you fix bases. When E and F are fixed, everything becomes unique. But if you take a different E and a different F, you get a different matrix. Right? How do we find the best one? That's what we're going to answer next. And it's going to be a topic that's going to extend over several lessons. It's a big discussion, a very practical one for applications. Very, very practical for applications, but we're going to have to build some machinery there. Okay.